choose people for whatever reason that's non-random. That's the majority of the studies you guys are going to be doing. Yep, you're going to have a selection bias to begin with. Because you're going to choose people off the street, or you've got a pre-formed group of some kind. Anytime you do that, the question you have to ask is, are they representative of the population you're looking at? The population is not all of humanity. The population could be college female rowers. That's a pretty specific population. Are they representative of college female rowers? College male basketball players? Or are they representative of the normal college student in a land-grant institution in rural America? Okay? So you can be very specific about it, but you have a bias. When you don't choose things randomly, you always have a bias in your study. So you need to think about what those biases are. We oftentimes call those limitations. And so when you do your studies, one of the things we ask you to do at the end is write down what are the limitations to what you found. Limitations are, I have a sample from the University of Idaho, without naming it, but a land-grant institution in a very rural, conservative state. Okay? That tells you a certain thing about that population. It's not going to be the same as if I go to South Carolina and I measure something in South Carolina. Okay? So you always have a bias when you go non-random. Did you have a question?
No, I was just.
Okay. Experimental mortality. This is when you lose people, and the key thing here is with non-random reasons. So if I'm doing a study, and all of a sudden I have a whole group of people leave my study, and it's not random, I've got a problem with experimental mortality. That's the first part. The second part is, in your study, you never want to lose more than 30% of your sample. So you need that, the magic number is 70%. So across everything we do, the magic number is 70%. So with mortality, don't lose anything more than 30%. You need 70% minimum in order to make some of the good conclusions. But give me some examples of things that you think could be non-random reasons if you were doing an experimental study with people.
You're putting them through a strenuous workout program, and like the people in just the high intensity group are dropping out.
Okay, so maybe the high intensity people wouldn't drop out. Maybe it's the low intensity people dropping out because they can't keep up with it. Is that what?
Or like, yeah, like say there was a high intensity program and like low continuous program, and people in the high intensity like interval group are dropping out.
Okay, so it's a non-random reason. So you got to go back and look at your treatment and say, is there something wrong with that? Okay, can you think of something else? What's another idea? Depending on what I'm doing, I could design a study, and in that study, I might, in some way, shape, or form, say something or do something that could offend a group of people in the study. Okay? So we might inadvertently offend somebody politically. We might inadvertently offend them in terms of their culture or their race, in terms of their socioeconomic status. There's a number of different things that people hold really dear to them, and you can offend them without even realizing you might not have purposely done it, but it's happened. Okay, so that's the non-random reasons. You can have random reasons. I did a study looking at the impact of exercise on pregnancy and fetal heart rate over 9 months. We had some people who left for random reasons. One that had toxemia. Another gained 76 pounds, and the physician did not let her walk at all. She had to be bedridden. So those are non-random reasons. Those are just flukes. Okay? All right, the last threat is expectancy. In the threat to expectancy, what you're doing is you're expecting one group to do better than another group. That's about trying to remove those biases. So if you design a program and you really believe in that program, and you know the people that are getting that program, you might expect them to do better better than what they really did. Or the results say one thing, but you write it in such a way as to sound like it is better than what it is. And typically, that's the second part that you will see. If you read an article that's an experimental design, oftentimes they did not find a very strong difference pre to post test, but they write it in such a way that it sounds like it's very profound. So an example would be, let's say, I'm going to draw this, I'm going to go back to, where do I get it? Oh, main page. Back here, there we go. All right. So if I go back here, and I have, let's see. I'm trying to think of one that I can use. Thought I had one a second ago. Give me just one sec here. My brain's a little slow here today. Oh, here we go. All right. Let me do this for you. Okay. I want you to think about this. I'm going to draw a line here, and 20 is over here, and 0 is over here. So I'm going to measure something. I'm going to measure moral reasoning. This particular scale that's going to be used goes between 0 and 20. And in this particular study, they wanted to see, is there a difference on this measure between people who have what would be considered a high level of moral development and people that have a low level of moral development. So what they did is they went out and they studied people that they thought had a high level of moral development. And that was people who were doing philosophy and moral philosophy, and people who were theologians, studying to be theologians. You would expect them to have a higher level of moral development because they're studying man's inhumanity of man. So you would expect that to happen. The people that you would expect to have a lower level of moral development might be freshmen in college. So that was their philosophy, okay, and their theory. So what they did is they went out, they did some stuff, they measured it, and what they found was that the people who were experts had a 3.15, and the people that were novices, those are the terms they used, had a 1.6. And when they ran a t-test between these things, they found that P was like 0.01. So it said it was statistically significant, because it's less than 0.05, difference between the experts and the novices. So they said the instrument measured what it was supposed to measure. And the study was able to differentiate between experts and novices. Given that information I just gave you, what concerns would you have about how they interpreted their results in terms of expecting to find things? What do you think? This is significantly different, 3.15 to 1.6.
But it's also like, if the scale's from 1 to 20, it's that much further.
Right, so if we have a 1.6 here and we have a 3.15 here, in the middle of the scale, what can you say about it? Where would you expect experts to be if you were actually having it happen? Where would you expect the experts to be?
Up near the 20.
Yeah, you would expect the experts over here, right? You would expect the novices over here. So what does it tell you? There might be a difference, but I'm expecting a difference. I'm talking about this difference being huge, but in reality, they're just novices on this particular measure, okay? So when we talk about the threats to internal validity, these are things that we can control if we think about them on the front end. They're things that if we randomize our study, most of the threats disappear. The threat to mortality, the threat to expectancy, those things don't disappear. Those you have to really think about and how do you control for those. So trying to remove your bias and so forth.
I had a question about this last one. So is this threat only relevant when you're actually writing up your final results and stuff, or is this when you're actually conducting the study as well?
When you're conducting the study as well. So I'll give you an example. I mean, it has to do with how you interpret your results, but it also has to do with how you conduct it. So an example of what happens is there was a guy, he wanted to see with those swim goggles, different types of swim goggles, how well do they work when you go down to 100 feet? So do certain ones work better than another? So he took these swim goggles, and he was actually the person who tested himself with these swim goggles when he went down. So he went down, did everything he was supposed to do, you know, in terms of compression and so forth, put on these different swim goggles. And then he came up and he said, these swim goggles are better than these swim goggles over here, and then these goggles and these goggles, right? So he was the person who did the test on himself. And do we have any swimmers in here? If you swim and you use goggles, every one of us have a different way in which our eyes are shaped, so there's different kinds of goggles that keep them from leaking. So he has one kind of goggle that fit him, and the rest of the goggles didn't fit. So he made the assumption all the rest didn't work. So he had a bias. He's expecting certain ones to work, and he was also using himself as a part of the bias. So he's in that expectancy threat. Okay? Okay, we're done.
Thank you.